First of all, because this is a science-oriented group, I'm going to introduce some physics, and I didn't hear a big groan, okay? So I hope it's okay. You won't need to follow physics in order to be able to understand the bulk of the lecture. Okay, but I wanted to introduce you to some of the equations and some of the basic concepts of general relativity in order to motivate those equations which are used to determine the age of the universe according to the Big Bang theory. Okay, to get the famous 15 billion years or 10 billion years age everybody knows. Now we're going to go to Newtonian cosmology. All right. Now, those of you who've seen just general physics, you know how to do an equation of energy conservation. Kinetic energy plus potential energy is remains constant. I'm not going to go through this whole thing. I'll leave it here partially as an exercise, but I will give you a quick run through. In the Newtonian universe, what you imagined was you had particles, you had galaxies, or whatever it would be, in a universe. We're talking about space-time itself. And they were clumping together, pulling together towards each other. You can compute what should be the velocity of some galaxy at the edge of this clumping, if there is such a thing, as it's attracted by all the galaxies within some kind of imaginary sphere within it. So this galaxy is being pulled by all these other galaxies in towards it. And you would then compute what is the speed of that galaxy falling in, or the acceleration due to the gravitational pull of all the other galaxies here. And you can do that a very easy computation. You simply do the kinetic energy term and the potential energy term. The kinetic energy. Okay, now I'm going to do a little bit of physics, as I promised. Okay, so you're all eagerly waiting. Where's the universe? The kinetic energy term, if r is the distance from the center of that clumping of galaxies, all right, so you have 1/2 mv squared, where v is simply the change, the derivative, the time derivative of this distance. So it's 1/2 m r dot squared, r dot being the derivative of r with respect to t. Okay, r dot is defined as the way you usually write derivative of r with respect to t. All right, so that's the velocity. So 1/2 mv squared over there is written as 1/2 m r dot squared. The dot is kind of right before the 2 squared. So that would be the kinetic energy. Then you add on the potential energy. The potential energy is simply gmn over r. Now, the energy is constant. We'll set it equal to 0. We can do that. Those of you who've taken gravitational physics in industrial physics will know exactly what's happening. It doesn't matter. This is the equation of energy conservation. This term plus this term is equal to 0. And one term is negative, because the gravitational potential is negative. Now, just look at that equation as a mathematical equation. What can you immediately see? You can cancel the n's out with a small m. Right? And then you get r dot squared is equal to 2gm over r. Well, that equation, the essence of that equation is that r dot squared is proportional to 1 over r. If any of you have done calculus, then you know that this is a relatively simple differential equation. The square of the first derivative of r is proportional to the inverse of that function. Some functions, when you take the derivative, it'll be a constant times that function. It could be any. This kind of relationship is satisfied by only one function. And that's a simple exercise that you can do at home if you want to. And it's r is equal to t to the 2/3. Okay, so the solution there, r of t is equal to proportional to t to the 2/3. That's the only function, t to the 2/3 is the only function which, when you take its first derivative and square it, you'll end up getting the same thing as if you just took 1 over it to begin with. All right, so it's not the mathematical riddle. Take some function, take its derivative, square it, and take that function and just make it 1 over, and you'll see you'll get the same result for both, doing both. So the Newtonian cosmology tells us that the function that is the radius of this particle falling into the center of the universe, its velocity is given by this function. All right, so we know that the answer is t to the 2/3. In Einstein's equations, when you solve these complicated equations and put in a complicated model, it's amazing, but the same model results, the same picture results. We interpret it differently. Instead of saying there's a galaxy and a clumping of galaxies and it's falling in towards the center, we're talking now about the universe as a whole, and the space is moving, so to speak. The space is expanding, and the distance between two galaxies is what's changing, not that the galaxy is actually moving. So if we come up with this equation, the Einstein equations, the r that we have there will be interpreted be the distance towards the center. It'll be the distance between 2 points because space is expanded. We end up with this prediction that space, this function r, now look at what I wrote, GR cosmology, Friedman, Robinson, Walker metric, ds squared is equal to minus dt squared. You see it like towards the top third of the page, plus r squared times the distance. That r squared is the one that we find through this simple exercise to be t to the 2/3. So in other words, the prediction of the equations is that the distance between galaxies, r of t, will have this kind of functional dependence on time. It's increasing with time according to this. The distance between galaxies is increasing with time that way. It's an amazing thing to be able to come up with an equation that tells you something so incredibly basic that you can actually then observe using telescopes and spectroscopic analysis and so on, and then find out that it's actually true. Now, what we want to do is find out, if that's the case, how long has the universe been expanding? In other words, if we extrapolated backwards and moved the movie in reverse, how long would it take till we got to there just being a point? All right? Now, the thing that can be measured is r dot over r. Okay? The quantity that we can measure using telescopes and so on is the relative velocity, the distance r between neighboring galaxies, let's say, as it changes, the derivative of it, the time, divided by the amount of distance. Okay, so it's like the relative velocity, the amount of velocity recession of galaxies, divided by the actual distance between the galaxies. That's a number that's measured, and that's now called the Hubble constant. So r dot over r is a measurable quantity called the Hubble constant, in the middle of the page, h, determined by observation to be, and then you have a number. Now, I'll leave this to you as an exercise. If you just simply plug in the numbers, you end up with the answer 10 billion years. And of course, you have to put in some constants, and it's a little bit more complicated, and that's where you get the exact fine-tuning. Is it 12, 15, 13 billion years, whatever. But very simply, from using Newtonian cosmology, interpreted within general relativity as curvature of space-time or distance between galactic points, you end up with a functional relationship that then predicts that it must be this. If you simply solve this equation based on what you can see, you come up with an answer of whatever, something like 10 billion years. And this is a beautiful theory that makes other predictions that have been verified, the cosmic background, radiation, and so on.